Hello everyone, and welcome to the presentation of my doctoral defense. My name is Matthias Häringer, and in the next 20 minutes I want to guide you through the main parts of my thesis. Low emission levels and limited thermoacoustic pulsation amplitudes, aka limit cycle amplitudes, are two important but often contradictory goals in the design of gas turbine combustors. To find an optimal design for both of these goals, we need to predict the thermoacoustic pulsation amplitudes or the limit cycle amplitudes already in the design phase of a combustion system. In general, we know that the compressible reactive Navier-Stokes equations here on the right include all the relevant physics. So in principle, we can resolve the entire combustor by means of compressible reactive LES simulation. We simulate the flow flame flow feedback here. We resolve the acoustics of the entire combustion system. And by that, we have a tool to model the limit cycle oscillation amplitudes. However, by looking at the length scales here of the flame and the acoustics, and in particular by looking at the difference of the length scales here, we immediately see that this cost is very expensive. And in the design phase, this is characterized by frequent modifications of the geometry and the flame and the fuel injection system, for example. We need to run a lot of these kind of simulations, and this means that this is just not practicable in the design phase. Of course, there are alternative approaches, and this one here is a very popular one. It is a two-step approach. In the first step, we just consider the flame, so one single flame of our system. We simulate that again with reactive CFD simulation, and we force that flame externally by broadband velocity forcing, and we record the output. And using system identification techniques, we can identify a reduced order model for the flame dynamics. In a second step, we combine these reduced order flame models with a reduced order model for the acoustics of the system. And by that, we form a self-excited system which we can use to simulate limit cycle oscillation amplitudes, for example. In order to simulate nonlinear phenomena, we need a nonlinear flame model, and that is the main problem of this approach. So step 2 is quite inexpensive. However, step 1, we need to have a general nonlinear flame model because we don't know anything about the system. We don't know about the frequencies or amplitudes of the system. So we need to have a nonlinear flame model which is valid for the entire frequency and amplitude range possible. This means a very expensive identification step here in the beginning, and this is also prone to overparameterization. Okay, so before considering alternative approaches to simulate limit cycle oscillation amplitudes, we first have a look at the system of interest, the systems we are actually interested in. In general, almost all modern gas turbines are either of annular or canannular type, and you see a sketch of these two systems down here. So in an annular type, you have multiple flames sitting in one common chamber, and each flame is fed by an injector, and the injectors are connected by the compressor outlet plenum. In a canannular burner, you have individual cans where you have one flame each, and these cans are connected by a compressor outlet plenum again, and a small annular gap in front of the first turbine stage. So these systems might look quite different, but they share important characteristics. First of all, they are multi-burner configurations, just meaning they comprise multiple flames. Secondly, most importantly, those systems have a discrete rotational symmetry. That means we can construct such a system by taking one single sector, or here denoted as unit cell, and just copying it around the circumference of the engine. And last but not least, these individual sectors or unit cells are coupled acoustically, which gives rise to azimuthal modes which extend over the entire circumference of the engine. All right, in this introduction, I wanted to show you that current thermoacoustic modeling strategies are impractical for the design phase of applied gas turbine combustors. And the question I want to address with this thesis is how can we reduce the computational cost while maintaining reasonable accuracy? And we will follow two guidelines throughout this thesis. The first one is we want to exploit the symmetry of the system of interest for us, so these cannular and annular combustors. And secondly, we want to use hybrid modeling strategies. And hybrid in that sense, we want to reduce our high fidelity simulation, in our case the CFD simulation, to an as small domain as possible. In our case, basically to the flame zone only. And all the rest of the combustor should be modeled by reduced order models. So all the acoustics, for example. And by combining those two guidelines, we end up at the title of my thesis, that is symmetry-enhanced hybrid thermoacoustic models of annular and cannular combustors. All right, so my thesis is made of 4 elementary building blocks. 2 building blocks are 2 symmetry-enhanced hybrid thermoacoustic models, which will be used to study limit cycle oscillations numerically. I will talk about those 2 models in a minute, so we will consider the other building blocks. Here we improved an existing calibration method for global reaction mechanisms. And this method allows the construction of small, cost-efficient reaction mechanisms for arbitrary fuels and operating points. This is especially important for new fuels like hydrogen or hydrogen fuel plants or ammonia fuel plants, for example, for which no global reaction mechanisms are available in literature. And such a global reaction mechanism is actually a prerequisite to even carry out or try out a simulation of an applied system like you have here. So even simulating one flame is impossible without having an efficient global reaction mechanism. Last but not least, we propose an adaptation strategy for experimental single can test rigs in order to tune the acoustic terminations of those single can test rigs in order to use those test rigs to the investigation of thermoacoustic properties of the full engine. And this strategy that we propose here avoids the very costly need for a full-scale cannular test rig for thermoacoustic investigation. All right. Due to the limited time, I will limit myself to those 2 numerical models. If you're interested in those other building blocks, feel free to read my thesis. Okay, before we go to the models itself, let's consider some theory. We already saw that our systems of interest have a certain discrete rotational symmetry with this unit cell you see again here. According to Bloch wave theory, the eigenmodes of such a system, the thermoacoustic eigenmodes, can be written in that form here, where we have a so-called unit cell solution, this psi, which is a function identical in each unit cell, multiplied by this phase modulation here. And this phase modulation is dependent on the number m, the so-called Bloch wave number, or also the azimuthal mode order. And this number m goes from 0 to n half, where n is the number of sectors or the number of unit cells our system is comprised of. This relation here has a very important implication in modeling because it allows us to reduce the computational domain to actually one single unit cell by employing so-called Bloch boundary conditions here. Those are pseudo-periodic boundary conditions for the acoustic variables, and they again depend on the azimuthal mode order and the number of burners that we have here. So with that, we can compute thermoacoustic eigenmodes of the full system by considering only one unit cell, and we compute those eigenmodes for each mode order. So for each mode order, we select an m, compute the eigenmode, and then select a different m. However, in our thesis, we don't want to compute eigenmodes, we want to simulate limit cycle oscillations, and the question here remains, what about the flame? So how to model nonlinear flame dynamics here? In our first hybrid symmetry enhanced model we propose, we follow a very straightforward approach, and we just use reactive CFD simulation as a nonlinear flame model. So we use the same approach as I showed previously, and we just directly couple a reactive CFD simulation with an acoustic reduced order model, which now includes the acoustics of the unit cell plus the symmetry condition. And by that, we formulate a nonlinear time domain model for one azimuthal mode order. And this allows the efficient prediction of limit cycle oscillations of this individual azimuthal mode order, of this isolated azimuthal mode order. However, there is one main drawback, and that is this model requires the Bloch symmetry, so it requires actually the discrete rotational symmetry of the system, so of the geometry, and also of the thermoacoustic modes in this system, even at higher amplitudes. And we will have a look at what this actually means, the symmetry of modes, in the next few slides, and if this is really a severe restriction of the model. So let's consider all the modes that show up in the system. Again, remember, these are the thermoacoustic eigenmodes that we expect. This is the mode structure, and now we go through all the M and consider just the mode orders that we see in the system. We start at M equals 0. This is the axial mode. This is the trivial case where all the burners do exactly the same. So this doesn't break symmetry, obviously. Secondly, let's consider the mode order M equals n half. This is the so-called push-pull mode. In this case, the adhesion burner have opposite phase, but they still have the same amplitude, and therefore still the symmetry is not broken in this system. Last but not least, we have all the remaining mode orders, so M equals 1 to n half minus 1. And in this case, we have so-called degenerate mode pairs. So these modes come in counter-rotating pairs, and it depends on certain nonlinear phenomena if these degenerate modes form a standing wave, a rotating wave, or a mixed wave in the nonlinear regime. And in this case, here I showed an example of a mixed wave, which is partly spinning, partly standing. And in this case, we have different phase in the individual burners, but also different amplitudes. And we know the flame has a nonlinear characteristics, and different amplitudes lead to different transfer behavior, which eventually breaks Bloch symmetry, meaning that in this case, the first model that we proposed is not applicable. So the model is applicable for all the cases except for degenerate modes, which occur as standing or mixed waves and eventually break symmetry. In order to circumvent this limitation, we formulate an alternative model. Here we once again start from the CFD, the reactive CFD simulation of one single flame, and we now connect it to a reduced order model of the full remaining system. And obviously this now includes other flames, and we have to model them somehow, and we again need nonlinear flame model. So in principle, we are in the problem I showed in the beginning. But now in this model, we want to update the flame models based on the observation that we have in our single vector CFD that we have here. There is one detail in this form, like you see the system here, the symmetry of the system is broken because we have a CFD here in this sector and the other sectors are modeled by flame models, and even if we update the parameters to match the CFD, it will never exactly resemble the CFD. Therefore, we do a trick. We just switch the CFD position and we include another flame model, and the CFD is now only solved in parallel outside of the self-excited system. And it's only there to adapt the parameters of the flame model. And in that way, the symmetry of the system is preserved. All right, so the main part is obviously this adaptation strategy, and we will have a look how we propose that in the thesis. In general, for the flame model, every parameterized nonlinear model is a possibility. In our case, we limited ourselves to a Wiener type model, And these Wiener type models have the feature that they have a well separation of a linear model block and a nonlinearity. And in this case, we have a dynamic linear model, which is in our case a flame transfer function. This has to be identified a priori, so before running the self-excited system. And this is identified by linear system identification techniques. And we have a static nonlinearity that corrects the output of the linear dynamic model. And now the parameters of the static nonlinearity are adapted on the fly here, these parameters S. And this adaptation is done as follows. We have our CFD simulation, which is solved in parallel with the same input as the flame model. And we just compare the output of flame model and CFD. And we use simple least squares optimization to find the optimal fit for the parameter vector S here. And by that, we fit the parameter for the single flame model. And then by exploiting the symmetry of the system, we know that all the flames should behave identically or should have the identical characteristics. And we just apply the parameters to all the flames of the system. All right, so now we have two symmetry-enhanced hybrid models, which are kind of complementary to each other. First, we have this so-called Bloch model, and this is a conceptually simple model, but it's less general because it relies on this isolated single azimuthal mode order, and it also relies heavily on the symmetry of the systems. And the second one, the ROLEX model, is more general because it doesn't rely on this symmetry as the Bloch model, but it requires more steps to set up, and most notably, it requires this linear identification step of the flame transfer function. However, keep in mind, this is orders of magnitudes less costly than identifying a general nonlinear flame model. All right, so now let's apply those two models, and we applied in our thesis, we demonstrated the capabilities of both models on two validation cases. First, we consider n equals 4 laminar canannular configuration, so a very generic case, where we get reference data from full 360-degree CFD. And secondly, we consider an n equals 12 intermediate pressure annular rig from NTNU, and there we have experimental reference data and basically the dynamic pressure measured here at these microphone positions. In both validation cases, the CFD domain of our hybrid models is limited to one single burner flame zone, and the acoustics are represented by a 1D network model, so a very simple setup. Let's first start with these generic laminar n equals 4 canannular burner. In the full CFD, we observe a stable limit cycle of an m equals 2 azimuthal mode. And if we compare that with the Bloch model, now for m equals 2, we see a very similar trend, and also we see that's the same trend for the ROLEX model. And for the ROLEX model, we obviously resolve all the burners explicitly, and so we can also compare the mode shape, and we see this characteristic feature of this push-pull mode that, like in the full CFD, the adjacent burners are completely out of phase but have identical amplitudes. The Bloch model obviously inherently has this assumption of the m equals 2 mode, so that's a non-brainer that this recovers the mode shape here. Just as a side note, the two other mode orders, m equals 0, m equals 1, give both a stable system with decaying amplitudes. So this is consistent in itself. Let's further consider the results in frequency domain and look at the amplitude spectrum of the heat release rate over a normalized frequency here. And here we compare the hybrid models in red versus the full CFD in blue. And we see that for both models, the frequency match exactly. and the amplitudes are a bit under-predicted by the Bloch model and a bit over-predicted by the ROLEX model, but all in all, the prediction is very good. Let's now consider this experimental test trick, the annular test trick here. From linear stability analysis, we see that the dominant mode of the system is an m=1 azimuthal mode order, so a degenerate mode at roughly 1600 Hertz. And this is also what we observe in experiment. There we observe mainly spinning m=1 mode order at this frequency. Our two hybrid models recover that, so they both give a limit cycle, a stable limit cycle of this mode order, the Bloch model m=1 here again versus the ROLEX model on the right. And let's have a look at two time instants. So for the Bloch, that's kind of boring, but for the ROLEX model, we can see interesting features. So in an early time where the amplitude is still growing, we see a kind of chaotic behavior here. But at later time, we see that all the burners synchronized in a very regular shape, and this is exactly what we expect for an n=1 spinning mode, where we have a certain phase shift between all burners, but a roughly identical amplitude. And this is what also is observed in experiment. Although unfortunately not for the heat release rate, so we have to compare the pressure at these two microphone positions I mentioned, and this is what is done here. So on top you see the microphone position M, on the bottom the microphone position L, and again the hybrid models in blue, the measurement in black, on the left side the Bloch model, on the right side the ROLEX model, and you see that again the frequencies match very well. The amplitudes are in both cases now overpredicted. The Bloch model less overpredicted than by the ROLEX model, but all in all, we see that the two models proposed yield a reasonable accurate result for the limit cycle oscillations, and that not only in this case but also in the other cannular burner, so in two entirely different setups. And at the same time, this is important to note here, the computational time or the computational effort that we need to simulate the limit cycle is much lower than with full CFD, because we only have to resolve the immediate vicinity of one single flame instead of here the entire combustion system. All right, I want to end the presentation where I began. I said at the beginning that currently there is no practical approach for predicting limit cycles in the early design phase of a gas turbine combustor. And this thesis tried to address this problem. So first, we improved the calibration method for global reaction mechanisms, which is beneficial not only for the developed hybrid models, but also in general for example, a 360-degree LES. We then proposed two numerical models, two hybrid models, and they allow a drastic reduction of the CFD domain. And now with those two models, the limit cycle prediction comes at reasonable cost. And this means that these models are now applicable in realistic systems and also in the design phase. And finally, we brought the learning from the numerical models, so the strategy we applied in the numerical models, to experimental testing. And the strategy proposed there offers now a way to avoid costly full-scale cannular tests, or at least reduce them, and thus again improves the design capabilities now on the experimental side. Right. Thank you very much for the attention, and I would be very happy if you want to read my dissertation. Thank you very much.